Good morning, everyone. I'm not sure whether it was a short introduction. I think it's my bio is on the homepage, but let me quickly introduce myself once more. My name is Philipp Bastians. I'm the sales manager for Life Science EM and XRM for Carl Zeiss Microscopy in North America. And my background is in the neuroscience world, so here and there you might see some neuroscience content. But today I'm gonna show you a little bit of some of the work that I did back a couple of years ago when I was still in the Asia Pacific region as a product and application sales specialist for volume electron microscopy as well as X-ray microscopy. And I'm showing you a little bit or I'm trying to give you an impression of some of the challenges that I had doing sample work for researchers and how I used various microscopy technologies to overcome them and eventually provide and create the data or produce the data that those researchers were looking for. All right, so I'll give a quick overview of volume electron microscopy in the life sciences. Next, I show you how these experiments can be done dramatically more efficient using X-ray microscopy. And then I will show you a couple of application examples where we correlated X-ray and electron microscopy data sets to eventually, again, get to those data sets of interest. So the field of volume electron microscopy seems to get bigger by the year, by the month. The overarching main workflows are indicated here with serial section or array tomography at the top, where we pretty much derive from the TEM world, cutting single, very thin sections of a block face, collect them on a substrate, can be on a TEM grid, on a cover slip, on a silicon wafer, and then eventually we use a scanning electron microscope to scan them off one section at a time, put those images together into a three-dimensional volume, and then eventually we derive a volume EM dataset. Serial block phase SEM, something that I grew up with for a very long time, doing that more than 10 years now, where we're using that microtome that in the TM world we use outside of an electron microscope, and we put that deli slicer into the vacuum chamber and do the slicing of the block face inside the vacuum, and consecutively always scan off the block face, not the section, but the block face, and the section gets removed so that we access the third dimension, again, acquiring three-dimensional data sets. And in a very similar way, we can use focus ion beam technology to, again, access the third dimension, slicing one section off after the other. But again, we are imaging here the block face consecutively, one block face at a time, and then put together a three-dimensional data set like the one on the right. So the workflow is, before we even put it into an electron microscope, requires some heavy metal sample preparation, putting, in this case, a mouse brain, expose it with heavy metals, put it into a resin block, and eventually we typically cut that sample down to our region of interest. And it always looks very trivial. We cut our tissue block out, maybe a tissue block of 2 millimeters, a millimeter, 2 millimeter. And eventually, in this case, I'm highlighting one of our new products that we launched recently, the Zeiss Volume, a serial block phase SEM system. Sorry, I have a little bit of background noise. I'm not quite sure whether you can hear that. I hope you don't, because the video has a little bit of audio. So the serial block phase system is, again, a microtome that sits inside the vacuum chamber. And what we are doing is, you will see the block actually right here, right, that we trimmed out of that mouse brain in this case. And there's the deli slicer, right, the diamond knife that comes in and sections off very, very thin sections. So it can be as thin as 25 nanometers. I mean, there are reported sections of 15, if not 10 nanometers in the field. And then we use a backscatter electron detector to scan off that block face, create one image after the other, and those get put together into a three-dimensional data set. So once the big block goes through the workflow, typically what we end up is with a data set of around 100 micrometer. And if we look at the right of a small cube of 100 micrometer of data, and to the left, which is multiple millimeters of often a tissue that we prepared, you realize there's quite a deduction of volume happening. And it always seems very straightforward to go from the left to the right. But there are many, many more possibilities to actually end up with the wrong spot of the sample, even in that intermediate state of that tissue block. And not only that, we need to be very conscious about the time that we spend on the tool, because it's still a scanning technology. We need to consider the cutting thousands of times, taking a section off of the diamond knife. And this can accumulate to a lot of time, a lot of experiment time. And often, again, research sits on smaller data sets. I mean, there are these ginormous big projects, right, that go for millimeters of data sets. But most of the research is actually done on fairly small volumes of data. So how do we make sure that this small block is actually capturing the structure of interest that we went out to get? So this is an example, and I had exactly that challenge with that sample a couple of years ago, working with a researcher at the National University in Singapore. They provided me with this classical embedded resin mold with some lag tissue and fat and muscle tissue of the mouse. And they handed that to me. I was like, they want to get the collagen network around a lymphatic vessel. I was like, yeah, that should be no problem. I guess we can do that. But if you look at that sample, again, it's really big. If we would acquire that all together with, and the idea was to do zero block phase SEM, acquire that whole data set, it would have accumulated to a lot of time. So I decided to go in a little bit more smarter with a roadmap and use our X-ray microscopy technology, where instead of an apple here, I would place that sample into the X-ray beam, project single images on that scintillator, translate that scintillator into actually visible light on the backside, and that we would magnify onto a CCD detector. We would rotate the sample as indicated here and collect many, many more of those projections. And by the end of the day, we can use all of those projections and computationally reconstruct a three-dimensional data set. And I'll leave it as simple as that. If you want to have more information about that, there's a slide at the end where I present quickly my team, and you can always reach out to them. And this is the data set that we got out of. These blobs that you see are actually fat. It's fat tissue. And then at some point you will see, oh, there's a cylindrical shape in the cross section, right? And I was like really happy because I knew now this multi-millimeter dimensioned sample, I know where to go for. So I presented that to the researcher. They're like, here's our vessel, and there's potentially the collagen network around it. And the researcher got back to me and said, like, that's true, that's a vessel, but it's a blood vessel. We need a lymphatic vessel. And the actual vesicle was down here. That's a lymphatic vessel. So it was really good for me to know. But without the insights of X-ray microscopy and having a holistic view of that data set, I would not have been able to figure this out just looking at that resin block. So there are the two vessels, and the low one, this what we went for. We put that sample eventually onto an aluminum pin. That is typically done for zero block phase SEM. And then I did a second X-ray scan to make sure, and we're scanning here virtually from the top to the bottom. Oh, and what I mentioned and forgot to mention is that X-ray technology and X-ray imaging is non-destructive. So the sample comes out afterwards just as we put it in. And you can see here in the video, the vesicle or the lymphatic vessel move from right to left. And here there's a little bit of a halo around it, and that's actually the collagen network that we were interested in. So then we moved it into our zero block phase SEM system, and I wanted to show you a little bit of correlation. You don't have to believe me. Those are the two data sets from the same sample. And if you look at the structure, for example, that tear here in that fat cell, the lymphatic vessel, and there are a couple of other features that you see in both data sets. So that should be a video, at least the other one. Well, doesn't play. But eventually, this is an overview data set where we also slice through and capture the whole overview. But eventually, what we wanted to see is the high resolution images of the collagen network. And this is, hopefully that video plays. It's something that you see here, right? With the endothelial cell here, and then some smooth muscles, and then the filigrane and integrated complex collagen networks and bundles that you can see wave around each other to eventually provide stability to the lymphatic vessel. Here's another example, and I'm pretty sure I'm running out of time, where we're also facing often the challenge of we want to go for a specific location in the sample. In that case, rice plant, the stamen of it, right? And we did pretty much the same, did the heavy metal preparation, put it into an X-ray microscope. This is the 3D view of it, where we can see the resin air interface, and that's really helpful feature to eventually prepare the sample and put it onto the pin. And then here's a cross-section view. Of course, we can reslice the 3D data set and look at the intricate details of that stamen. And then eventually we will put it into serial block phase SEM. What I want to point out here, the video stops at some point, is that I placed the field of view that we imaged of the whole block phase at exactly the location that we wanted to capture. So I wanted to reduce the amount of area or volume in that sense scanned that is not useful. So we captured here that head of that anther and try to be extremely resourceful in not scanning too much more, because scanned area is time. And if that is not information that we need, well, then it's wasted time. Lastly, I want to show a little bit of a research work.
Now, Philip, you have plenty of time. You have more than 10 minutes left.
I got more than 10 minutes. Oh boy, then I ran through a bit too quickly, but I hope there are more questions then coming my way. Wonderful. Thanks, Tom. So this is some research work that I helped peripherally with a researcher that I was with in the Max Planck Institute back in Frankfurt, Yunfeng Hua, here from the Hua Lab. What he went out is to image the cochlea of the mouse auditory system. And he faced a very similar challenge, that cochlea is quite an intricate structure, and not all the area in the cochlea was interesting to him. For his specific research, he wanted to go in and look into the innervation, the specific innervation of the inner hair cells. So to be very precise and also consider it with his time and having effective scanning, he went in and captured an X-ray microscope data set first of that whole cochlea. Next, he used that information to trim down the sample to a very specific location. And what's very interesting, at least I didn't know that before he taught me about the research, is that there is a tonotopic map along the snail house of the cochlea. So at different locations, the inner and outer hair cells, they sense different frequencies that eventually the mouse is hearing. So he could, with the X-ray information, he could actually very precisely go in and not only map the tonotopy of that cochlea, but also go in at the right location of the eventually frequency that he was interested in his research specifically. And then after the preparation, using X-ray information, he mounted it again on this aluminum stub and continued doing serial block phase SEM and acquire the inner hair, outer hair cells, and especially the innervation and the fibers that eventually innervate those or receive information from those hair cells. So these are two views, reslices of that three-dimensional X-ray data set. And on the left side, you actually see I think it's called the tympanic membrane, right, which is vibrating whenever there's a sound eventually hitting the cochlea. And eventually down there, you can replay the video, there are the outer hair cells, and this area here is the inner, or is the location of the inner hair cell. And when that tympanic membrane vibrates, there are those small stubs from the hair cells, literally the hairs, that are eventually getting vibrated and moved, and which opens ion channels and eventually creates a signal that can be picked up by the auditory nerve. So if we look at the reslice here on the right, you can see here those three lines, right? The three outer hair cells and the inner hair cells, and that already on the level of X-ray microscopy, just to give you an impression of how much resolution we can pull out of that system. So we have a very, very detailed view of where those inner hair cells will be in the context of that whole cochlea. And then lastly, I didn't run through too much because Tom reminded me just now I had another 10 minutes. This is eventually the resulting data set out of the serial block phase SEM. Getting the tympanic membrane up here, the three palisades, or looks like palisades, like three pillars here on the right with the outer hair cells. You can see the hairs on top, right? And then eventually the inner hair cell, which is sitting here, and all the innervation that's happening at the base of those inner and outer hair cells. All right, with that, I do a quick summary. I introduced a little bit what technologies are available in the volume EM world for life sciences. I focus a little bit more on serial block phase SEM, because that's the technology that, in my opinion, is the one that allows you to, in a most straightforward way, acquire three-dimensional data sets. There are more considerations to it. That's not the only one. But the challenges that I face for serial block phase SEM, finding the right locations, were tremendously supported and facilitated, I would say, with our X-ray microscopy technology, allowing us to get a holistic view first, and then go in in a very targeted way to acquire eventually the structure of interest. And then lastly, I showed some of the core work that is out there. It's continuously done, and there's much more research of that sort in the publication record. And lastly, I want to take the opportunity quickly to not only introduce my team, because a couple of folks on the slide you will already know. I think Joe Maury is in here in the call as well, right here on the right. I think half a year ago, he gave a presentation as well. I'm sitting in Dublin. It's very early morning for me still. Dublin, California. It's always mixing up things. And 6:30 in the morning for me. And eventually we have another specialist in the team, Steven Hernandez, who's sitting in Phoenix, Arizona. And you might also know Aubrey Funk, our product marketing manager, specifically for our life science EM and XM business segment. All those folks are what we like to call customer facing, so in the field. There's a much bigger team behind all of us, with application specialists and scientists eventually here in our demo center, and also traveling to eventually train users on our scopes. And with that, maybe there's another follow-up presenter who enjoys a couple more minutes that I might have left over. And if there are questions, please keep them coming. I see Alice's hand rising right away.
All
Morning,
right.
Alice.
Hi, Philip. Very good talk. Actually, I have a little bit of challenge question. I don't know if you can answer or not, but looking at your presentation is very promising. As I know that X-ray microscopy is really useful when you try to search a sample in the dark black resin block, right? And the thing is, once you look at the image inside block, then you know where it is your region of interest. Then you still need to take out, try to figure out how to trim in to get it. It is possible. I know Zeiss is leading in here, and to somehow install like a laser cutting or whatever cutting machine inside the X-ray, so that you can do like a guiding the way you can trim to the area you are there. Then that will save a lot of effort for the other people.
Correct. So no, we don't have a laser ablation system inside the X-ray microscope system. We do actually have one on one of our FIBSEMs, and there is some work I think that was done with the Crick Institute in London, where they actually carved out, guided by the X-ray microscope data, pillars actually for serial block phase SEM with the laser ablation system. I can forward you the publication about that. Typically, the way I utilize the X-ray microscopy data is applying ultramicrotome cutting steps in a very precise manner. You can set the steps, the cutting thickness, and of course the number of cuts, and then hone in from the various directions. And yes, it's not a nanometer precision cutting tool, but it allows me with an accuracy of around 5 to 10 micrometers to capture actually the structure of interest on my aluminum pin for serial block phase SEM. And what I always do is a second, and those scans are fairly quickly. They take no more. And if you want to have just an overview, in less than half an hour, you have another scan of your resin block sitting on top of the aluminum pin that we typically use for serial block phase SEM. So there's always another confirmation scan with the X-ray system. And that allows us to have the data set of the X-ray system aligned, at least in the vertical axis, with the serial block phase imaging that we will do afterwards. And that makes it very easy and provides me always with a preview, a low resolution preview of what I will be seeing during my CO block phase SEM experiment. And that is what allows me to set the region of interest, my imaging field of view, at the right location to capture eventually while the knife is cutting through the block at the right portion of the sample.
Thank you.
You're welcome. Thanks for the question. Always happy to take challenging questions. I think there's two more hands up. Mark?
Yeah, hi. When I saw your cochlea work, it got me thinking about, in the volume tome, got me thinking about the bone and whether your sample was calcified or decalcified. And I know that we have Helmut here as a speaker, and I'm just wondering, first of all, was it calcified or decalcified? And when you're generating data sets with thousands of shavings of the block face with the diamond knife, let's say it's a diatom knife, how long does that knife last? And you know, I know it depends on the type of material, but how frequently is a volume actually interrupted by knife marks and so on?
So that sample specifically, I went into the methods just to double check on exactly that question. It was decalcified. So that takes a lot of sting away already from the diamond knife. But since we have an expert from Diatom, and I'm trying to be very careful, he might have much more experience. He will have 100% more experience than I do with diamond knives. Again, I'm referring back to the X-ray data, allowing us to also see where's the bone. This is what we most of the time do with our X-ray systems, actually imaging bone in the life sciences. So we can identify that very precisely. And that is also something that we can, or some specific material, some specific volume of that big block that we can cut away. So with X-ray microscopy, it allows you to also remove those challenging aspects of the sample that might be a challenge down the road for the diamond knife in this case.
Well, Philippe, that's all right. I'm actually a bone researcher, so I want calcified bone. But anyways, we do have a bone talk coming up, yeah. Maybe or something more. Thank you very much.
You're welcome. Thanks for the question. And then I think I see another hand up. Matt?
Yeah, hi, Philip. I have a question about and apologies if this is something that you've kind of been to already, but what kind of level of technology in terms of X-ray microscopy do you need to do the kind of things that you're talking about? Because I know that you know, if you have an X-radier, then that's ideal, of course. But for kind of just navigating to some extent, you know, is somebody that has access to a low resolution system going to be able to do a lot of what you've talked about? What kind of level is needed, and is it going to be feasible to use a cheaper system to do this? Right.
I really like that, and that was back in the time. Well, back in the time, I mean, a couple of years ago, was always to be a big challenge for us. Our Versa X-Radia Versa system that you're referring to, it is, I'll just call it that way, it's not cheap, especially in context of some of our volume electron microscopy solutions that we are offering as well. So my team and I, the one that I presented, I think the slide before, we are working quite tremendously now on getting our context, we call it the context X-ray microscope system, which doesn't have that X-Radia Versa optical magnification system included. It can be upgraded to that, but that makes our X-ray system, the context micro CT, this is really a real micro CT, meaning there's no second resolution, what we like to call resolution at the distance magnification behind that scintillator. It uses a flat panel. And I was just working yesterday night after I prepared some of the slides here on another sample that we have in-house in our demo facility, using only that context, that pure micro CT technology. And I'm really amazed how far you can even push the resolution with that micro CT based system. That I need to add that it's not a tabletop system. It is still as heavy, as massive as our X-Radia Versa system. But that provides the stability and that resolution capabilities that we need for that research. And it comes at a much cheaper price tag as well. So I'm really excited, and going forward, I hope Ruqing and Tom lets us, one of us here on the slide, talk again down the road, showing you some of the micro-CT context data which we use for these correlative experiments with array tomography, with CR block phase SEM or FIB-SEM tomography. And that makes it what we hope for much more feasible in terms of having access to it, in terms of how fast we can scan and what kind of volumes we can acquire, but at the same time providing the researchers doing a follow-up volume EM experiment the resolution they need to trim the sample at the right location and to have that preview that I mentioned just now for any of those volume EM experiments that they are doing. I hope that gives you a little bit of an idea. It was a challenge that we identified a long time ago, and our micro-CT is more than capable. I mean, there's some really great data coming out of our tool. Can't share it yet. It's the first permission of the researcher, but it's really stunning.